Okay, it's 2:26 a.m. Do you know where your divergence is? Okay, well, we have the divergence theorem. And I'm just going to state the divergence theorem, which we have proved in a plane. But this goes on into 2 and 3 dimensions. Okay, and it simply says that the integral of f dot n over a surface, which is the flux through the surface, f dot n, remember, is the component of the vector field perpendicular to the normal, perpendicular to the surface, f dot n being the component perpendicular to the surface. And that's just the flux through the surface. When we integrate that over the surface, we just add up the flux over the entire surface, and we get the result. And in doing so, we get the same thing if we integrate the divergence over the entire volume. So the total divergence within the region is what we get when we do the volume integral, and that's equal to the flux through the surface. Now we've seen this in 2 dimensions. We have a picture where we've got a curve in 2 dimensions, and we got the region bounded by the curve, and we have flux through this curve. Sometimes the flux is normal to the curve. Sometimes it's more nearly tangent to the curve, and the closer it is to coming through the curve, the closer it is to being normal, the bigger the component of the vector function perpendicular to the region. Integrating that around the entire curve, we get the integral of the flux. And now, by analogy, if this is a surface instead of a curve, so it encloses volume, and we have a region inside the surface, the volume region, we can integrate the divergence of F over the volume and get the flux through the surface, and vice versa. To illustrate what this means, and maybe a little bit about just how useful and important it is, we're going to use the same region that we became acquainted with in a very recent video clip. Okay, the region bounded by the triangle with vertices at 1, 0, 0, 0, 2, 0, 0, 0, 3. We're familiar with this, and it serves as a good example. Okay, we recall that this surface is represented by, is part of the plane x plus y over 2 plus z over 3 equals 1. The specific surface can be described as z equals 6 minus 6x minus 3y, which is what we get if we solve this equation for z. X going from 0 to 1 and y from 0 to 2 minus 2x. Now let's use the function f of x, y, z shown here. Looks like, that square root of x squared minus y squared looks like it might be kind of a nasty function to integrate. Our normal to the surface is as it was in the previous examples, easily found by taking the gradient of the left-hand side here to be 6i plus 3j plus 2k divided by 7, the magnitude being 7, giving us the unit normal vector. Okay, now we want to look at the integral of over the surface of f dot n ds. Now f dot n, remember, is the flux of this function. So if we were to graph this function at every point of the surface, at some points the function might be parallel to the surface, contributing nothing in that region to the flux. Some points it might be perpendicular to the surface, so the flux would be equal to the entire value of the function times the neighboring region. And at other points, and most likely almost everywhere, it's going to make some angle with the normal vector. Okay, the integral then over the surface of f dot n ds is going to be what? It's going to be, first of all, an integral over the region in the xy plane, the integral from 0 to 1 with respect to x, and from 0 to 2 minus 2x with respect to y. Our ds, our surface increment, is going to be 7/2 of our dy dx increment for reasons we've seen recently, simply because n dot k is 2/7 and we divide the dy dx by the n dot k. And f dot n is easily enough calculated. We just take the dot product of this with this. We've factored out the 1/7, and then we just have 6 times our xy, 3 times our y squared, and 2 times our negative square root of negative 2 times our 2 times our negative square root of x squared minus y squared. We can do that, and I'm just putting an etc. down here. This would not be an overly difficult integral, but it would be somewhat complicated because of the square root of x squared minus y squared and all that stuff, and then having to plug back in the expression for y, which is going to get more complicated. So this wouldn't be bad. It would be feasible, but maybe not really easy. As an alternative, we can integrate the divergence of this function over the volume enclosed by this surface, the volume between the x-axis and the surface. Now this is going to be a relatively easy integral, as we're going to see. But I've got to back up. I said something. What I've done up here is incomplete. So I'm going to say S1 is the surface of this triangle. In order to apply the divergence theorem, we have to enclose, we have to have the surface, the entire surface that encloses the region, so that we would also have to consider the integral in the yz plane of this part of the surface, and the integral in the xz plane of this region, and the region of the xy plane itself. These would all be parts of the boundary of this surface. So if we wanted to do the surface integral, we'd have to do a little bit more work. We'd have to integrate, we'd have to find the integrals of this function dotted with the normal vector over each of these triangles. That's not particularly difficult to do. It's probably a little easier than this was, but still it's extra work. Okay, I've quickly written down the descriptions of these surfaces. They can be described by inequalities. We get pretty obvious integrals, but again, it would take a little bit of work to do these, so that the integral here would be the integral over this, plus the integral over S1, plus the integral over, make that S2 plus S3, plus the integral over S4, and I'll put just some ellipses in here to indicate that we'd have to add these to this in order to get the total integral. Again, none of these would be difficult, and they'd probably work out a lot nicer than this one does. Now again, our alternative is to integrate the divergence of F with respect to the volume over the volume enclosed by these four parts of the surface. Okay, the divergence of F is really easy to calculate. We just take the partial of xy with respect to x, that's y. Partial of y squared with respect to y, well, that's 2y. Partial of negative x squared minus y squared with respect to z is 0. So we get a simple expression here. Our region D is straightforward to represent in terms of inequalities. Z is going to go from 0 to 6x minus 3y as we go from the xy plane, from a point in the plane, up to the surface. And then the region is